Okay, dear students, welcome to my video class. This is a continuation of photochemistry, and I hope you have watched the last video about the Frank-Cotton principle and selection rules for electronic transitions. Anyhow, we can move to these topics. The diagram on the board is called the Jablonsky diagram. Jablonsky diagram describes the fate of excited molecules. The fate of electronically excited molecules. The diagram tells you what will happen after a molecule be excited electronically. What will happen? What is the fate of that molecule? This discussion is very important when we go to the details of photochemistry. Okay, in the full screen, I have the diagram and the data will be written somewhere here and there. Okay, this is ground electronic level. These are the different vibrational level. This is ground vibrational level in ground electronic level. This is the first vibrational level. This is second vibrational level. This is third vibrational level. Everything in ground electronic level. And this is second electronic excited level, S2. S means singlet. Singlet we have already discussed. This is the meaning of singlet. And S2 is the second excited electronic level in singlet state. These are the different vibrational level in that electronic level. This is S1, that is first electronic excited level. First electronic excited level. These are the different vibrational level within the S1. This is triplet. Triplet is something like that. Parallel spin. Parallel spin. Okay, and different. This is also the excited level and more energy level than the singlet ground level. But there are also different vibrational level. Okay. Now, this is fluorescence. This is phosphorescence. We will discuss. IC means internal combustion. ISC means inter-system crossing. Inter-system crossing. Okay. Yes. Now, what happened to an excited molecule, electronically excited molecule? There are two phenomena. One is non-radiative process. Non-radiative process. Second is radiative process. Radiative process. That is, third is reaction, chemical reaction. After the excitation, after a molecule being excited, it will undergo any of these three. Any of these three. Maybe it will undergo non-radiative processes and will come down. Or radiative process and will come down. Both may happen or it may give the reaction. If it gives a reaction, that is called photochemical reactions. Okay. Now this diagram discusses both radiative and non-radiative processes. Okay. You know, non-radiative process means it undergoes the de-excitation through non-radiative way. There are some example of non-radiative is internal combustion, inter-system crossing, vibrational relaxation, relaxation. These are relaxation. These are non-radiative processes. Radiative processes is a de-excitation ways, de-excitation methods where during the de-excitation it emits the radiation. It emits the radiation. There are two types of radiative de-excitation methods. One is fluorescence, second is phosphorescence. In non-radiative processes, it will undergo the de-excitation. It will emit their higher energy through these ways, and heat will be produced due to these processes. Heat will be produced. Be careful. Heat will be produced. In non-radiative processes, through non-radiative processes when molecule de-excited, what you will get? Tell me, what you will get? You will get the heat. When radiative ways, molecule undergo the de-excitation, what shall you get? You will get light. That lights are divided into two categories: fluorescent light or phosphorescent light, or fluorescence or phosphorescence. First, we can say that in the ground level, molecule can be excited into any electronic levels. That is not forbidden. But it will be excited from singlet to singlet. And there is no direct excitation from singlet to triplet. Singlet to triplet excitation is forbidden. We'll discuss that. Because during the excitation or emission, the electronic state should be preserved. Singlet to singlet, triplet to triplet, or doublet to doublet. Okay, fine. For more details, you will watch that video. Anyway, this goes to any other level, that is second or first or any other electronic level, but it should be single. Now, from normally the excitation begins from ground to vibrational level of ground electronic level. From the ground to vibrational level of ground electronic level, that is the most lowest energy state. From that, it goes to any vibrational levels of a given electronic level. Any vibrational levels of a given electronic level. Suppose a molecule is reached to highest vibrational level, it goes to the lowest vibrational level within the state. Lowest vibrational level within the state. This arrow sign. This happens because of the collisions of molecule between each other. Suppose a molecule in the higher vibrational level, in a given electronic level, it will collide with another molecules. Because of that collision, it loses some energy. And because of that loss of energy, it will go to the lower vibrational level within this electronic level. That kind of loss of energy because of the collision and comes down to the lower vibrational level is called a vibrational relaxation. What is the vibrational relaxation? Right, my student. If an excited molecule in the higher vibrational level of an excited electronic level collide with another molecules and loses energy in the form of heat and goes to the lower vibrational level within the electronic level. Within that electronic level is called vibrational relaxation. Once again I will tell you, the excited molecule in higher vibrational level of an excited electronic level undergoes a collision with another molecules, due to the collision energy losses and comes to the lower vibrational level within the electronic level. That process is called a vibrational relaxation. Now another one is, what is internal conversion? Internal conversion. Yes, this is the internal conversion. Internal conversion means, suppose you have a different, this is S2, and this is S1, almost this same. Okay, that is, it is the shifting of molecule from the lower vibrational level of higher electronic level. Once again, from the lower vibrational level of higher electronic level to a higher vibrational level of lower electronic level. Fine. It is a shifting of the molecule from the lower vibrational level of higher electronic level, that is S2, to the higher vibrational level of lower electronic level. This is called the internal conversion. And because of that transition also, heat is emitted. And in that level also, you can have vibrational relaxation like this. Okay. Now what is inter-system crossing? Inter-system crossing. Inter-system crossing. Inter-system crossing. That is, suppose you have a, suppose you have a S1, you have a T1. It is the shifting of the molecule. It is a shifting of the molecule from the lower vibrational level of singlet excited state. It is a shifting of the molecule from the lower vibrational level of singlet excited state to a vibrational level of triplet excited state. That is called inter-system crossing. It is the changing or transition from lower vibrational level of singlet excited state to the vibrational level of triplet excited state. Okay. Because of this also heat is generated, therefore inter-system crossing also non-radiative processes. Now what is fluorescence? Fluorescence is a radiative emission. Radiative processes. It is the countdown. It is the countdown or emission of molecule. Countdown of the molecule from lower vibrational level of singlet excited state to the any vibrational level of ground electronic level. It is a come down of or emission of molecule, come down of molecules from the lower vibrational level to the any vibrational levels of ground state electronic configuration. Because of that, light is emitted. Suppose the lambda fluorescence, that is the wavelength of fluorescent light, because of this emission a photon is emitted. Wavelength of that photon will be greater than wavelength of absorbed. This one. Am I correct? Yes. Lambda absorbed. This is smaller than this. Or frequency of this greater than this. Because it is absorption has higher frequency than fluorescent emission. Because the energy gap is smaller. Fine. This is a fluorescence. Now, what is phosphorescence? It is the come down of molecule from the lower vibrational level of triplet excited state. Triplet excited state to the any vibrational level of ground electronic level. This is the lambda fluorescence and this is a lambda phosphorescence. Therefore, lambda phosphorescence is still greater than wavelength of lambda phosphorescence still greater than fluorescence. That is still greater than absorbance because this is higher energy gap than this, which has higher energy gap than this. Now, Stokes shift. There is a word Stokes shifts. Stokes shift is the difference between lambda excitation or lambda absorption and lambda fluorescence. I said you this is smaller than this, and the difference is called Stokes shift. Stokes shift. That is, I will tell you. Suppose what happens? Okay. Suppose students, I draw a peak like this. Suppose intensity versus intensity versus wavelength peaks, wavelength increases. I got a very sharp peak like this. Okay. This is the suppose this is the lambda excitation, lambda absorption, and this is the lambda fluorescence, and this is the lambda. This peak is for lambda phosphorescence, and this difference is called the Stokes shift. And the fluorescent peak will be broad enough, because during the fluorescence, more number of photons are emitted in a small period of time. Because I said in the excited, singlet excited state, the lifetime is very small, like 10 raised to minus 15, minus 15 second or minus 12 second. But here 10 raised to minus 1 to 10 raised to minus 4 seconds. Lifetime in the triplet excited state. That a molecule can stay at the triplet excited state in 1 second or 0.1 second, like that. But it is very small time. Okay, therefore in a small period, lot of photons are emitted. Therefore its intensity will be little high. But it will be broad spectrum. Okay. Yes. Therefore this is all about our fluorescence and phosphorescence. Fluorescence and phosphorescence. And fluorescence is called phosphorescence is called delayed fluorescence. Why phosphorescence is called delayed fluorescence? Because it is like a fluorescence. Light is emitted, you will see the light, but it happens after some time, because it has high resting time at the excited level. Okay. And phosphorescence most probably at a visible radiation, because its wavelength is higher. Therefore it is around the visible light, that is 400, 700 and like that. Okay. Suppose the excitation happen in the UV radiation, fluorescence and phosphorescence will happen at the visible radiations, visible region. Because the wavelength of excitation is smaller than fluorescence, which is smaller than phosphorescence. I hope this video is helpful and understandable. If you have any doubts, let us discuss. Okay, thank you.